Hello, I'm Sam. So I'm going to answer the question of where Snell's law actually comes from, because I don't think it was particularly well explained when I was at school. It seemed to be one of them, just sort of given equations, and I think it's also quite a useful exercise in trying to think about waves in general. So we're going to have a problem like this. So we'll have a wave incident on this flat interface between a refractive index region 1 and region 2, and we'll say that n2 is greater than n1. And this is our wave vector here. And the main point of solving this problem is to think about the continuity of the field at this boundary. So the condition that we need is that the k vector x component, or the periodicity in the x component, has to be equal on both sides of the interface. And what that looks like is this, where what I'm saying here is the x component of the k vector in region 1 is equal to that of k2, of region 2, sorry. So how do we work this out? We know that wavelengths shrink when they move to regions of higher refractive index. So if we're taking our wavelength in a vacuum to be lambda naught, then this is the wavelength in region 1, and then this is the wavelength in region 2, and the corresponding wave vector magnitudes will be the reciprocal relation. So k2, n2, k0. And then, so this is our drawing of k1. This is our angle to the normal, and what we want to work out is what the angle is on this side. So in order to get the x component of this k vector, we basically need to subtend in this direction here, and that corresponds to the sine of the angle. So what we've got is k1x is equal to n1 k0 sine theta 1, k2x n2 k0 sine theta 2, and then when we equate these two, we have what we wanted. Bang. So geometrically, what are we saying? This k1x, this kx matching is basically saying that we want this distance between wavefronts in the x direction to be equal on both sides. So the distance between these two dots. If we know that the wavelength is getting smaller, going to this higher refractive index region, then what has to happen is this wave direction needs to change so that it goes closer in towards the normal, and then the corresponding distance on this side will be this. And then if my drawing was anywhere near accurate, then those two distances would be the same. Yeah, so that's the geometric way of looking at it. Another cool thing, but well, doing the same calculation, you can basically work out what the allowed angles of propagation are if light goes through a diffraction grating as well. I'm not going to go through it, but basically the difference is that there are multiple allowed angles, and by working those out, then you get the diffraction equation. Cool, thanks for listening.